Hey grade 12s, and welcome to question 8 to 10 of this paper. So this is the Maths paper 2, May to June 2024. So our first question 8.1 is a proof. Now I do have these proofs on my channel, but I'm going to still go ahead and work on it here in this paper just because it is an official June paper. So we have 8.1 and it says, in the diagram, chords AB, BC, and AC are drawn in the circle with center O. DCE is a tangent to the circle at C. Okay, so the question asks us to prove the theorem which states that the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment, i.e. angle BCE is equal to angle A. So we just really have to prove that BCE, this angle, is equal to angle A. Okay, so first of all, there's some constructions that we need to do. This is for 5 marks. So the constructions we need to do first of all is you need to join OC. But the way you're going to join OC is you're going to join OC and extend it to a point, and we can call that point P. Okay, so let me make that a construction line. Okay, so we're extending it to P. And then you have to, now you see, because we're trying to make this angle equal to this angle, this is our focal point. We're going to focus on this side. And so because of that, what we're going to do is, so we're going to join AP. Okay, so now our constructions are done. So in your exam, they're probably going to give you the actual diagram and you can construct on it. So we're going to name these angles. We're going to call that angle C1 and that's angle C2. So you see, you're going to use these angles here. And then that is angle A1 and angle A2. Okay, so now that we have everything, let's just write down what we constructed. That's all. Okay, so construct CO extended to P on the circumference and construct line AP. That's all we're doing. So the first thing we're going to do is, when looking at this, I want you to see that, you see this arc PB? It is supporting this angle at the circumference, angle C1, and it's also supporting another angle at the circumference, angle A1. So that would mean that they're equal because they're supported by the same arc. So we'll say that means angle A1 is equal to angle C1, right? So those two are equal, and our reason would be angles in the same segment are equal. Okay, so now that that is down, we know those two are equal. Okay, so these two are equal first of all. Then the second thing that I want you to take note of is that OC is a radius, okay, from the center to the circumference. And if you have a radius and a tangent, the radius is always perpendicular to the tangent at the point of contact. So it means that we have perpendicular here. Okay, perpendicular lines are there. So we're going to go ahead and tell them OC is perpendicular to DE. So OC is perpendicular to DE. And that's because the tangent is always going to be perpendicular to the radius at the point of contact. Okay, so that would mean that this angle here is equal to 90 degrees. But let's write it like this. Angle C1 plus angle C2 would give you 90 degrees. So that's just the conclusion. Angle C1 plus angle C2 is equal to 90 degrees. Now, if you look at this diagram, there's also another angle that we have equal to 90 degrees. So this is a diameter, right? And you know that the angle supported by a diameter is supposed to be equal to 90 degrees. So we have another 90 degree angle there. So that is this. This is also 90 degrees. So we can tell them that angle A1 plus angle A2 is also equal to 90 degrees. So A1 plus angle A2 is equal to 90 degrees. But the reason for that, it's not really angle supported by a diameter. You can say angle in a semicircle. So angle in a semicircle. Okay, so angle in a semicircle equals 90 degrees. So now we're actually kind of done with looking at the diagram. It's now the equations. So do you realize that we told them that A1 and C1 were equal? But you see that when you add these, they give you 90. So if these two are exactly the same, then that would mean these two are the same as well, since they must add up and give 90 degrees. Okay, so really what I'll say here is, but we know that angle A1 is equal to angle C1. So that would therefore mean that angle A2 must be equal to angle C2. Or let me rather say angle C2. The reason why is because we're focusing on the bottom first. Is equal to angle A2. So now that we have shown them that, do you see that angle C2 is that angle BCE that they were referring to? So that means that BCE is equal to, and angle A2 is that angle A they were referring to. So we're just going to call it angle A as well as they did. Is therefore equal to angle A. And there we go. That is proven. So that is for 5 marks. Moving on to the next question. Okay, so 8.2 says, in the diagram, PQRS is a cyclic quadrilateral. Okay, so they've already told us that. With RQ being equal to RS, so these two lines are equal. Then they tell us that ST is a tangent to the circle at S, and SR is produced to N. Then they lastly tell us that angle R2 is equal to 68 degrees. And the first question is to determine with reasons the size of angle P. Okay, so angle P is this angle over here. Well, they told us that this is a cyclic quad. So remember, the exterior angle of a cyclic quad is equal to the opposite interior angle. So that's what that is. So this is 68 degrees as well. We'll just tell them that angle P is equal to 68 degrees because of the exterior angle of a cyclic quad. Okay, so that is it for that question. Moving on to the next question. The next question, 8.2.2, says we have to find the size of angle Q1. Okay, so angle Q1 is this angle over here. So, do you notice that? Remember they told us that SR is equal to RQ, right? Those two lengths are equal. So it would mean that this is an isosceles triangle. And so the angles right opposite those equal sides would also be equal. So that would mean that angle Q1 should be equal to angle S2. Okay, so in this one, that's already given. So I won't actually mention it for them. I'll just tell them the angles that are first of all equal. And there's a reason I'm saying, let's look at that. Because do you see now that when we look at this triangle RSQ, that this angle 68 degrees here, this R2, is the exterior angle of that triangle. Okay, it's the exterior angle because it's an extension of one of the sides of the triangle. So it's the exterior angle. The exterior angle is equal to the sum of the two opposite interior angles. So here is a way that we can just show them so that it's structured. We'll tell them that angle S2 should be equal to angle Q1, right? Those two are equal. Let me rather say angle Q1 is equal to angle S2. Okay. And now that we know that, the reason is because we have angles opposite equal sides. Okay, angles opposite equal sides are equal. Okay, now that we know that, we can go ahead and tell them that because this is an exterior angle, that angle R2 is equal to angle S2 plus angle Q1. Okay, so angle R2 is equal to angle S2 plus angle Q1. Let me rather say angle Q1 plus angle S2 because of the exterior angle of a triangle. Okay, so there's our reason. So do you remember that we said angle Q1 and angle S2 are equal? So it means that in this equation, I know angle R2 is already equal to 68 degrees, so I'll replace it. So I'm saying that 68 degrees is equal to, well, we said that angle Q1 and S2 are equal, but we're trying to find angle Q1. So we can say angle Q1 plus, but because we know these two are equal, let's replace angle S2 with angle Q1 as well. So this means that we're saying 68 degrees is equal to 2 angle Q1. Then divide both sides by 2 to solve for Q1. Therefore, it means that angle Q1 is equal to 34 degrees. And there we go. That is the size of angle Q1. Okay, moving on to the next question. Then the last question in question 8 is find the size of angle S1. Okay, so remember we found these two, right, to be 34 degrees each. So 34 and 34. So what would angle S1 be? You see, when you're looking at angles, ask yourself where it is. Angle S1 is between a tangent and a chord, so you can use the tan chord theorem on it. So the angle between a tangent and a chord is equal to the angle supported by that same chord. So that means that angle is this angle 34 degrees. See? There's the chord SR, and this is the angle supported by SR. So that's also 34 degrees, okay, because of the tan chord theorem. So angle S1 is equal to 34 degrees. S1 equals 34 degrees because of the tan chord theorem. Okay, so these are the two reasons that you can use depending on what your teacher accepts. And I say what your teacher accepts because that's in the case that you are in grade 12. So your teachers would be marking the June papers. So that just depends on what your teacher is going to accept. Okay, so this is the full reason and that is the shorthand reason. Okay, so that is the end of question 8. And then we move on to question 9. Okay, so we're on question 9, and question 9 says, in the diagram, AB is the diameter. So AB is the diameter of the circle with the center F. Then they tell us that AB and CD intersect at G. And then FD and FC are drawn. Okay. Then they also tell us that BA bisects angle CAD. Now that is very important. You need to know what the word bisect means. Okay, but we're going to work on that when they ask us that. And then they also tell us that angle D1 is equal to 37 degrees. So the first question in all of this is determine, given reasons, any 3 other angles equal to angle D1. So other angles equal to D1. First of all, I see lines that cross like this. So do you see BG? BG is a chord and it's supporting the angle at the circumference, angle D1. Then if you look for another angle at the circumference that it also supports, it would be equal to that angle. So BG is also supporting the angle at the circumference, angle A2. So you see how you're going to look at those angles because you wanted to find out what else was equal to D1. You ask yourself, where is D1? It's at the circumference. So use theorems about angles at the circumference. Okay, so that's the first one we have. We find that this is equal to A2. Let's go ahead and put that down. So we're saying that A2 is equal to angle D1 because of angles in the same segment. So I'm also going to tell them, yes, it's also equal to 38 degrees because of angles in the same segments are equal. If you want to use the long reason, is the angles at the circumference supported by the same arc, in this case, are equal. Okay, so that is the first angle we have. Now I see that because we have A2, remember they told us something about this big angle CAD. They said that BA bisects CAD. You see, when you intersect, when something intersects another thing, it just cuts through. That's all. When something bisects another thing, it means it cuts it in perfect half, okay, into 2 equal parts. So if they told us that BA bisects this angle CAD, it means that it cuts it into 2 perfect halves. So this angle should be equal to that angle, okay? So that is another angle equal. So angle A1 is equal to angle A2. So I'll tell them angle A1 is equal to angle A2, and you know that angle A2 is equal to angle D1. So the reason angle A1 is equal to angle A2, well, I'm just really not going to. Let me just say angle A1 equals angle A2 first, and it's because of BA bisecting CAD. Okay, and because of that, of course, that means that angle A1 is also equal to angle D1. So we're just finding all the angles equal to angle D1. So we found 2 angles so long. So that is also 37 and 37. What else is equal to 37 degrees? Okay, if you look at this, you see when you're looking at these angles, apart from asking yourself, where are they? Okay, they're at the circumference. You can also ask yourself, what are they part of? So with that being said, I see that this is part of a triangle. Both of them are parts of triangle. So we can even focus on this one. You see that that is a triangle. And do you see that FA is from the center to the circumference? So that's a radius. That is also a radius. So they will be equal in length. Because they are equal, it means that the angles opposite their equal sides are equal. So you have an isosceles triangle, and that is equal. Okay, so first of all, I'm going to tell them the sides that are equal because this is not something that is obvious. You have to tell them it's because it's equal radii. So AF is equal to CF, first of all. AF equals CF, and the reason is because they are equal radii. And then after that, I can tell them that angle C2 is equal to angle A2. So therefore, angle C2 equals angle A2 because of angles opposite equal sides are equal. Okay. And so, of course, that means that angle C2 is also equal to angle D1. So angle C2 is also equal to angle D1. So that would be 3 angles. So that's also 37 degrees. 3 angles that are equal to angle D1. So that is the first question. Moving on to the next question. Question 9.2 says, show that DG, that line DG is equal to GC. Okay, so they're saying we need to show them that this is equal to that. Okay, when looking at this, I feel like, because the thing is, if you're trying to show that 2 lines are equal, it's kind of like saying that this is a bisector, it's bisecting that. But there's no way to prove that, oh, that is bisecting. Okay, there's no way to actually do that unless to prove to them that these 2 are equal. So why don't we look at it from this angle? These 2 lines are part of a triangle, right? They're each part of a triangle. So GC is part of this triangle, and you can see DG is part of this triangle. Okay, so what do you notice about these 2 triangles? Well, they both have 37 degrees. Okay, so I can already see that these 2 triangles are going to be congruent. We just have to prove it to them. That's all we have to do. So we have to prove that the 2 triangles are congruent. So first, we already have these 2 angles being equal. Then the second thing is AG, right, is a shared side in these 2 triangles. So we have 2 things being equal. We just need one more thing. We're trying to prove these 2 lines are equal. They never told us that these 2 are equal, so we can't really assume things yet. Okay, so here's how we can do that. Okay, do you also notice that here we have another triangle? We have a little triangle here, this triangle here, and it's also made up of FD, which is a radius, and FA, which is a radius. So it means that angle A1 must also be equal to angle D3 because this is an isosceles triangle. So we can start off there. If we find that angle, let's go ahead and do that. So angle D3, first of all, tell them that angle D3, well, we should tell them the sides that are equal first. So we can start off by telling them that AF is equal to DF, AF equals DF, and this is because they are equal radii. So 2 radiuses. So we have equal radii there. Then it means that angle A1 should be equal to angle D3, or D3 equals A1. So therefore, angle D3 is equal to angle A1, which is of course equal to 37 degrees because of angles opposite equal sides are equal. Okay, so now that those 2 angles, we found that, I can just erase the blue and the purple. I don't really need that. We're just focusing on those 2 triangles. So now we know this is equal to 37 degrees. All we would need to find, well, we would just need to find these 2. We just show them that these 2 are equal as well. So if we can show them those 2 are equal, then it of course means that this whole angle is equal to this whole angle. Okay, so angle C is equal to angle D, definitely. And to show them that those 2 are equal, you see that we have FC, which is a radius, and FD, which is also a radius. So we can show them, first of all, those 2 radiuses or radii are equal, and so we have an isosceles triangle again. Okay, so let's go ahead and tell them FC. So FC, let me start on the next line. FC should be equal to FD because these again are equal radii, and so because of that, these 2 angles are equal. So angle C1 is equal to angle D2. So therefore, angle C1 equals angle D2 because of angles opposite equal sides, which I already copied. So we have that now, angle C1 being equal to angle D2. I said C2, D2. Okay, so now that we have that, because they're exactly the same thing, and these 2 are exactly the same, it means that that big angle ACD is equal to ADC. Okay, so that's the conclusion because we know now these two are equal and we have 37 degrees. Okay, so at this point, we've shown them that this entire angle is equal to this entire angle. So why were we trying to do that again? Remember, we are trying to prove to them that GC is equal to GD. So in this triangle, let's just mark them. That's the blue one. And let's mark this one yellow. So there. In these two triangles, now we can see things that are equal. We can prove that these two triangles are congruent. So I have to start off by saying, okay, so I just pulled it down, pinned it to the screen so that we can still work on it. So now that we've shown that those two angles are equal, we can finally go ahead and prove that these two triangles are congruent. So I'm going to just say in triangle, and let's call that one AGD, so AGD, the yellow one, and triangle AGC, the blue one, AGC. So first of all, the angles we have already equals angle A1 is equal to angle A2. And that's because those two have already been proven. We've already proven that they're equal. So proven angles. So we have that. And then what else do we have? We have this line, right? That is being shared between these two triangles. So that is AG. So AG is equal to AG. That is a shared side. So shared side. And then lastly, we have these two angles being equal now. So ACD is equal to ADC, ADC, and that is proven already. I feel like we were supposed to write this here, but okay. That is a proven angle that we have there, but our reasons are up there anyways. So therefore, it means that triangle AGD is congruent to triangle AGC. So when triangles are congruent, all their corresponding sides and angles are equal. So that means that DG, let me just say it the way they said it. Yeah, DG is equal to GC. So that means DG is therefore equal to GC because of congruent triangles. And there we go. Okay, so that is it for that question. Then we move on to the next question. The last question for question 9 says, if it is further given that the radius of the circle is 20 units, calculate the length of BG. Okay, so the radius of the circle is 20 units. Let me bring the diagram down. So let's just remember now we have these two sides being equal. This is equal to this. Okay, I'm going to have to try to write thin so that everything can fit in. So we are told we need to, if it's further given that the radius of the circle is 20 units. So everywhere you see a radius, it is going to be 20 units. Then they told us to calculate the length of BG. So we need to find BG. Okay, so let's look at this. Well, if we know the radius is 20, then it means that this entire thing would be, the diameter would be 40 units. So, I don't even need to look at it like that. I can look at it like this, right? BF. I know BF is from the center to the circumference, so it's a radius. That's 20 units. So in order to find BG, I just need to find FG. If you find FG or GF rather, GF, then you'll find BG. So let's actually focus on finding that FG or GF. How would we find GF? Okay, remember we just showed them now that these two lines are equal, meaning we have the situation of, and that's in this paper law. This is actually there in like trigonometry, I think, or analytical geometry. You see that we have the line drawn from the center of the circle to the midpoint of the chord. Okay, it was analytical geometry. Okay, to the midpoint of the chord, that line is going to be perpendicular to the chord. So let's actually do that first because it's going to help us so much if this is a right angle triangle to be able to find that since we know the radius. So we can show them that that is actually 90 degrees. We know the radius is 20 units, so FC is 20 units. All we would need is to find that we can use trigonometry. We can use trigonometry to find this by finding the angle C1. If you find angle C1, you can use one of the trig functions to find FG. Okay, so all maths is related. You can use Euclid in analytical geometry. you can also use trigonometry here as well because they're all about math. So let's go ahead and look at what we're going to do here. Okay, so I'm going to first of all tell them that CFG, right? FG is perpendicular to CD. And that's because the line from the center to the midpoint of the chord is perpendicular to the chord. Okay, so now that we have that, we can go ahead and show them that that is perpendicular. Okay, because we have that being perpendicular, we have a right angle triangle. And in this right angle triangle, the only thing we really need now is this little angle here. And we know we can find that knowing now that in this triangle, CGA, or we can call it ACG, this triangle has 37 degrees, it has 90 degrees, and it has this entire angle. So we can find angle C1 using the sum of angles in a triangle. So let's go ahead and tell them that we're going to say angle C1 is equal to, I'll say 180 degrees, and then subtract by all the angles inside the triangle. So minus 90 degrees, minus the 37 degrees, and that other 37 degrees. So minus 37, minus 37. Okay, so let's see what that gives us, angle C1. And as you can see, that gives us 16 degrees. So angle C1 is equal to 16 degrees because of the sum of angles in a triangle. I have to write narrow because I need the page to be here. Okay, so now we know that is 16 degrees. That helps us a lot. And we have a right angle triangle. So look at how we can find this length, FG. We can find this by saying FG, we know now we're looking for that. And that is the opposite side of this triangle, this right angle triangle. So that's opposite. And then the only other length we have in this triangle is FC, or the only other length that I'm seeing now is FC, which is 20 because it is the radius. They said the radius is 20 units. So we have the radius. So as you can see, that is the hypotenuse. So we have the opposite and hypotenuse. So which function can we use? We can use sine. So I'm going to say sine of 16 degrees is equal to, and we're going to say that is the opposite over the hypotenuse. So sine 16 degrees is equal to the opposite side, opposite of hypotenuse. So that is the FG. So FG over the hypotenuse, I'll just say of 20. So the reason is trig function of sine, I guess. Okay, and now to find that FG, remember we just need to find FG so that we can find BG, because we can see that BF is a radius and we know the length of it already is 20 units. Okay, so here I'll just multiply both sides by 20. So times 20 and times 20, and FG, you see that these two would cancel. I'm just going to leave it like this because this is not the final answer. The final answer is to find BG. So FG is 20 sine of 16 degrees. Let's leave it like that for now. So we just know that we have found FG. So again, FB is a radius. Okay, so that's a radius, and the radius is 20 units. So FB is a radius. Okay, so I can also just note that down. Tell them that FB is equal to 20 units, okay, because it's a radius. And since we have that being equal to 20 units, then we can just say to find BG, you simply must just say, take the whole of FB minus FG, and you'd get BG. Okay, so I'm going to go ahead and tell them BG comes about by taking the entire length of FB and subtracting it by FG, which is equal to, and so we're going to say FB, which is 20 units, the radius, minus that other part, which is 20 sine 16. So 20 sine of 16 degrees. Okay, and we will find the length of BG like this. Okay, so I'm saying 20 minus 20 sine 16. Okay, and I get decimals, which is 14 point, since the paper says round off to 2 decimal places, so 2 decimal places, that rounds up to 9, so 49 units. And that's my answer there. They don't say anything else about rounding off, so That's going to be our answer. Okay, so that is it for question 9. And then we finally move on to question 10. Okay, so we are finally on question 10, which is the last question for this paper. So question 10 says, in the diagram, COD is a diameter. It's the diameter of the circle. COD is the diameter of the circle with the center O. Then we are told that EA, right, is a tangent to the circle at F. So that is very important. Then they also tell us that AOC, right, that is perpendicular to CE. So as you can see, we have a right angle there. Then they tell us diameter COD. COD produced, okay, so this is just the other info. Produced intersects the tangents to the circle at E, okay, just intersects there. And then they also tell us that OB produced intersects the tangent at the circle at A. OB is just produced intersecting the tangent there. And then CF intersects OB. CF just intersects OB. Okay. And what else do they tell us? In T. And then they tell us that CB, BD, OF, FD are drawn. So those are just chords and lines that we have there. Okay, the first question is to prove that TODF is a cyclic quadrilateral. Okay, let's go ahead and talk about cyclic quadrilaterals quickly. For you to prove that something is a cyclic quadrilateral, there are 3 ways to do this. So the first way is if you have this scenario. So if you have a quadrilateral and you notice that the exterior angle of this quadrilateral is equal to the opposite interior angle, then it's a cyclic quadrilateral. The second case is if you have, again, well, not really a quadrilateral, but we have a shape like this, something like this, where there are 2 angles at the circumference sharing a chord, okay, that they're being supported by. So 2 angles at the circumference supported by the same chord, and those 2 angles are equal, then it's a cyclic quadrilateral. Okay, so those 2 angles are equal. And then the third way to prove that something is a cyclic quadrilateral is if you have a quad and you notice that the opposite angles of this quad add up to 180 degrees, then this is a cyclic quadrilateral. Okay, so those are the 3 ways. So let's look at TODF and see which way would suit that shape. So TODF is this, TODF. When you look at that shape, which one do you think you can use for it? Now, I'm already going to cross this one out. The reason why is because I saw lines going nicely across and I was like, oh, okay, maybe we can use that. But yeah, those lines are not, you see, that line is going there. And then this line is the only one connecting the 2 points on that quadrilateral. So definitely not, we can't use that. Okay, that's out of the picture. Okay, it's down to these 2 now. Well, this one is not a good idea because it has to add up to 180. They did not give us angles. There are no angles here. So that's out of the picture. Can't use that. Now we would have to look at this one. The thing is, it may not be out of the picture, but this is how I rule it out. This is usually the most basic way that they would put it, okay, if they don't want to complicate things. So let's look at that. Let's just see. Do we have any exterior angle in this quadrilateral? Yeah, well, we have one here. But that would mean that this must be equal to this. And I don't like what's going on here. You have a division of angles. So I'm not even going to consider that yet. Let's look at something else. Okay, I see this here. This is 90 degrees. This is the extended line of this quadrilateral. So that's an exterior angle. And it should be equal to the opposite interior angle. It's also doing the same thing. But that's fine. That's good. The reason I'm saying that's fine is because do you see that COD is a diameter? If this is a diameter, the angle supported by a diameter in a circle is equal to 90 degrees. So that angle from F2 to F3 is 90 degrees. And that is the angle perfectly opposite in that quadrilateral. So there we go. That's how we would prove that. We'll show them that this is 90 degrees as well. Okay, let me just put it like that so it doesn't fear with any angle there. Okay, so that's what we can tell them. Tell them that angle F3 is equal to 90 degrees. So it's equal to 90 degrees because of angle in a semicircle. And because it's equal to 90 degrees, it therefore means that angle F3 is equal to that exterior angle, angle O1. So angle O1. And so that therefore proves that TODF is a cyclic quadrilateral. And the reason for that would be because the exterior angle of that quadrilateral is equal to the opposite interior angle. Okay, notice how I didn't include the word cyclic quadrilateral in the reason, because I'm just saying the reason that it is a cyclic quadrilateral is because the exterior angle is equal to the opposite interior angle, okay? So, of that quadrilateral. Okay, so I just added that. Okay, so that is it for question 1. It's 4 marks. And we move on to the next question. Okay, next question 10.2 says we need to show that or prove with reasons that angle D3 is equal to angle T1. Okay, so show them D3 is equal to T1. Let's look at that. Okay, how can we get there? Well, you see, one thing that you should always do, remember what you just concluded. You concluded that this shape is a cyclic quadrilateral. So you can use all the properties of a cyclic quadrilateral on this shape now. So with that being said, do you see that T1 is vertically opposite T3, right? So those are equal. And T3 is the interior angle of this cyclic quadrilateral. And you see that D3 is an exterior angle, okay? Because it's DF or TODF, right? So from there to there, that is an exterior angle. D3 is the exterior angle. So okay, so it's first of all because T1 is equal to angle T3. So tell them that angle T1 is equal to angle T3. And that was because of vertically opposite angles. Okay, and so since those two are equal, you see that we have a cyclic quadrilateral. They told us that is a cyclic quadrilateral. So angle D3 should be equal to angle T3. Okay, because it's the exterior angle of that cyclic quadrilateral. So angle D3 is equal to angle T3 because of the exterior angle of a cyclic quadrilateral. Okay, and so that will therefore prove that since they're both equal to T3, you see, it shows that angle D3 is finally equal to angle T1. Okay, so that was for 3 marks. Moving on to the next question. Okay, so let me just also mark those properly. So I don't really need this lining of the shape. I just need to show things that are equal. So I'm saying those two are equal and that is equal to that. It's very important that you do that because once you find certain things, you may need it in the other questions. Okay, so the next question. So we need to show them or prove that triangle TFO is similar to triangle DFE. You see that in our diagram, they never gave you any lengths. There's no lengths at all. So we can't prove triangles are similar because their lengths are in proportion. We're going to have to just show them that their angles are equal. So let's go ahead and just highlight those. And I'm going to bring this drawing down. Okay, so triangle TFO, that is this triangle TFO. And triangle DFE, so the triangle over here, DFE, that bottom one. Okay, so let's see. First of all, in order to prove that these two are similar, we have to just prove that all their angles are the same. The good thing is we have an angle that is the same in both of them. You see that T3 and D3 are equal. So we only actually have to prove one more angle. If we can find one more angle, then by default, the third angle in the triangle is equal. So let's just go ahead and find that one more angle. Where is that going to be? Let's see. Okay, I see something. So you see that you have to actually focus on one angle. You can either decide to focus on F2 or O2. I tried O2. But then I just kept on trying to find out what other angles add up to 90 degrees as well. And I didn't really see that here because you see E is just like outside. It's not a very nice angle to work with. So I decided to focus on F2 really. If you look at F2, do do you see that OF is a radius, right? And OC is also a radius. Then you have a triangle here. So that makes that triangle an isosceles triangle. And so the angles here would be equal. The angles opposite the equal sides are equal. So now that we know that F2 is equal to C2, if you look at this, you see that in your blue triangle as well. Remember they told us that this was a tangent, and that's one thing. You should always go back to the scenario and just see anything you might have missed. Because this is a tangent, the angle supported by the tangent and the chord, which is F4, right? Angle F4, is going to be equal to the angle at the circumference supported by that same chord. And if you put your finger on D and F and you trace, you see that that angle is C2 as well. So what's actually happening is F2 is equal to C2 and F4 is also equal to C2. So that would make F2 and F4 equal to each other. So now we just have to write it down and show them. So we are saying that angle F2, first of all, is, well, I can't really say that yet. I have to tell them about the radius. So I have to prove that these triangles are similar. Let me actually just start by writing it. In triangle TFO and triangle DFE, what we first have is, remember we already had that T3 in that triangle TFO is equal to angle D3 in the triangle DFE. So angle T3 is already equal to angle D3. That one is proven. We've proven that. So it's a proven angle. Then after that, now we're actually showing them the second angle that is equal. The second angle is equal, first of all, because we have OF being equal to OC because they're equal radii. So OF equals OC equal radii. Those two radiuses are equal. Because they're equal, the angles that they have will have an isosceles triangle now. Now their angles are equal. Okay, so angle, that means that angle F2 is equal to angle C2 because of angles opposite equal sides are equal. Okay, and then now that those two are equal, we also just go to F4 and you see that in angle F4, I'm just writing them together, not skipping a line because it's all the same story really we're talking about here. So angle F4 is equal to, you see it's the angle between the tangent and the chord. So angle F4 is equal to angle C2, the angle at the circumference supported by that same chord. So that's angle C2. It's interesting how what they wanted you to prove, right? Like your proof, the theorem you had to prove has a lot to do with the diagrams that we find. And I've noticed that pattern. So angle F4 is equal to angle C2 because of the tan chord theorem. I know I said the full theorem already before, so I'll just call it tan chord here because of that tan chord theorem. And so now because F2 and F4 are both equal to C2, it means that angle F2, right? Oh, let me put in this in the right order. So TFO, right? TFO, yeah, it's F2. So F2, angle F2 is equal to angle F4 because they're both equal to angle C2. So in the two triangles, those two angles are equal. Then these two angles are equal. And then lastly, because those two angles are equal, by default, the third angle in each triangle is equal. So this is now equal to this, meaning, let me put it a different marking. So 2 strokes. That means that angle O2 by default should be equal to angle E. So angle E, because they are each the third angle in a triangle or in the triangles. So there we go. Remember that third angle in a triangle is really just because if you add it up and you know that angles add up to 180 degrees, then these two will end up being exactly the same since those ones are equal. Therefore, it means that they are similar. So triangle TFO is similar to triangle DFE. Okay, DFE, and the reason for that is angle, angle, angle. Okay, so that is that question, and it is for 5 marks. And we finally move on to the next question. Okay, so I don't really need all those lines for the triangles. I just need the angles that are equal. So just can get rid of those. We don't need those. And this is all we need really, just showing the angles that are all equal. Okay, so moving on to this question, 10.4. I think this is the second last question Okay, so the second last question says, if angle B2 is equal to angle E, we need to prove that DB is parallel to EA. Okay, let's get our diagram. Okay, so here is our diagram. And they told us that angle B2 is equal to angle E. So let's mark that. So B2, let's put 3 lines on it, is equal to angle E. Angle E. And the question is for us to show them that, or prove that DB is parallel to EA. Interesting. Okay. You see, for you to prove the lines are parallel, you can use fun angles. So, for example, if I have lines and I don't know whether they're parallel or not, and I find out that, let's say this is X, and I also find out that that is also X. If those two are equal, do you see that they form alternate angles? I'm drawing it the wrong way. Alternate angles, right? And because you have alternate angles, it would mean that those two lines are parallel. So if you can find any fun angles on those lines, then it will prove that that is parallel. Meaning, well, we know that this is equal to that. If you can show them that B2 is maybe equal to A, then your lines are parallel because that would give you corresponding angles. You see, that is an F thrown upside down. That angle equals this angle. Okay, let's see. What can we actually use on this to prove that those lines are parallel? Okay, likewise, if you can also prove that, you can also focus on proving that angle D1, right, is equal to angle E, because that also forms an upside down F as well. That's also an F, so corresponding angles as well. So there are multiple ways. Let's just see how we can actually do that here. So one thing I don't see alternate angles. Not really seeing that. And that's fine because like even when you want to form it, it doesn't really have angles by the places you want to form it at. So I think we can just stick with corresponding angles here. Okay, I see it already. So here, you see this is OD, this is OB, right? That forms an isosceles triangle. So those two angles must be equal. OB is a radius, OD is a radius. So you have an isosceles triangle. So this angle D1 is equal to angle B2. See why it's very important to draw on it different colors and different markings for your angles. So that's where it comes from. So you can go ahead and tell them OB is equal to OD because they are equal radii. And since they are equal radii, the angles opposite equal sides are equal. So angle D1 is equal to angle B2 because of angles opposite equal sides. Equal, of course. So that has the same marking now. It's also equal. Because of that, now also just to make it make sense, I will tell them, but you guys told us that angle B2 was equal to E, right? Angle B2 is equal to E. This is not that important, but I just put it like a conversation. So if you guys told us that angle B2 is equal to E, then that means that angle D1 is now also equal to E because they both equal to the same thing. You see, D1 was equal to B2 and B2 is equal to E. So that means that angle D1 is equal to angle E, and that forms your corresponding angles. Okay, so I can therefore tell them that DB is truly parallel to AE. So DB, they call it DB. DB is parallel to AE, EA. Why are they spelling like that? Okay, EA. And the reason is because we have corresponding angles are equal. Okay, I say the corresponding angles are equal. That sounds better. So there we go. And we've proven that. And then we're finally on the last question of question 10, which is 10.5. Again, I'm going to erase all of these because I've already proven that. So I'm just going to tell them these two lines are parallel. And we're just going to have to remember that. So we have all our angles now. The last question, 10.5, says prove that DO is equal to TO times FE over AB. Don't freak out when you see things like that. Okay. All they're doing is they're just using one of the things you've already proven. Okay. It could be the similarity, because that's one thing we proved. We already proved that those triangles were similar. And it could also be, as you can see, you see what is going on here. You have parallel lines. you have a triangle. That's the proportionality theorem. But I'm not going to jump to conclusions. We'll try both. It's just like trial and error. So I would usually focus on the thing that I have proven before. But then again, I could also use that. It just depends. Let's just see how this works out. So first things first, mark out the lines that you see. You see, they say DO. So I'll mark that out. DO. Okay. Then they say TO. Where's TO? TO is here. Mark that out. Then they say FE. So FE, I'll mark it in the same color. FE. Here. And then AB. These are funny looking lines that they're using. You'd expect it to use, the proportionality theorem nicely, but it's not really doing that. Okay. So I wanted to use the proportionality theorem on it, but this AB is what's going to stop me from doing that right now. And this EF, because, it has this. That's nice. It has DF. And if it at least had DE, then I'll be like, okay, I can use that. But let's think about that though. Shouldn't DE be equal to AB? They should be equal. The reason I say they should be equal is because remember, these lines are parallel now. And if they're parallel, angle B2 should be equal to angle A because of corresponding angles as well. And because it's equal, right, you have angles being equal in a triangle. It would mean that those sides are equal. Okay, the two opposite sides of that triangle would be equal. Okay, but I don't want to jump around looking for things. Let's actually just look at this in a more structured way. So that would have been a good idea because we can actually show them that this line OE is really equal to OA because you already know that OD is equal to OB because that's two radiuses or radii. And then if these two are really just equal, that already means that in this triangle, because you have two angles being equal, their two opposite sides would also be equal. But the reason I don't want to use that is this is now stopping me. For me to use the proportionality theorem, I need OD and then I would need DE, right? But then the side opposite it, I would also need OB and BA. And you see, nowhere did they mention OB. They mentioned OT or TO, not OB. So I don't think the proportionality theorem is good here. Also, where did this EF come from? Okay, if we look at this again, it doesn't seem like they're using proportionality theorem. It looks like they're using the sides of those triangles that we proved are similar. Because you see, the one triangle was this one. The other triangle was this one. So in the purple triangle, you see that OT is being used. And in the yellow triangle, this is being used. But then the question would be, where is this one coming from? Okay, that's not difficult. OD is coming from OF because OF is part of the purple triangle and OD and OF are both radii, so they're equal to each other. So it's very possible that they're using those triangles. So the minute I already start seeing that, I'm going to go ahead and bring my triangles. And when I say bring my triangles, I really just mean this. I will work on the conclusion. I'll go to the conclusion and take it like this so I can get the proportions. So I know these triangles are already congruent. I'm going to use it like this. So we can go ahead and start by getting the proportions. So I'll say TF over, I think this is, so TF over DF. And so I use TF and DF should be equal to FO over FE. And then that should be equal to TO over DE. Okay. And now I'm going to see the sides that we have and compare it to what we have here, and also the triangle, of course. So the triangle is going to be very important there. Let me just bring it down here. Okay, so here's our shape again. And I'm going to now just compare what we have here because we need to just have all of these here. So to know which pair I should use, like should I use these two or the first and the last one together? I'm going to just compare the sides that we have here with what we have here. Here we have DO. Now we don't have any DO here, so it must mean that DO was replaced with one of the sides in the triangles. So let's just see that. DO, we already spoke about this. DO is equal to FO or OF, okay, FO. So do you see that FO is there? And I'm just going to put here that is probably the replacement for DO. So that's how we're going to look at it. And then if, we get all the sides in two pairs, then you know that they use the similar triangles. The next thing we can look at is TO. Do we have TO here? Yes. So it's already probably these two. Well, let's see. And then FE. Yeah, we also have FE here. And then AB. We don't have AB, we have DE. Let's see what B is here. AB is this line. And DE is this line. So yeah, that makes sense. Remember I said that these two are actually definitely equal because you have an isosceles triangle. Well, we will have an isosceles triangle, okay? Because these two angles are going to be equal since you have this angle here should be equal to that because of corresponding angles. Okay, so there is a way for us to show them that DE is actually equal to AB. So we do have that, okay? They replaced it with AB. So now we just have to fix those because we know this is what they used. So I'm really just telling them that before actually telling them that we hold on to that. We know this is because of similar triangles. Let's go ahead and prove these ones. So since they used DO instead of FO, I'll show them that DO is actually equal to FO because of equal radii. So equal radii, those ones are equal. And the second thing I need to show them is this DE and this AB. How are they actually equal? Okay, so we're looking at that triangle. Again, remember, you have here corresponding angles. If you look at it, it's an upside down F since these two lines are now parallel. So it means that angle A is equal to angle B2. So first of all, tell them that angle A is equal to angle B2 because of corresponding angles. Okay, so we have that because that is equal to B2 and you know that B2 was already equal to E, okay? That means that, I can just say, just continue it like a conversation. But angle B2 was already equal to angle E. So that means that angle A is equal to angle E. So because those two are equal, you have an isosceles triangle. And so that means their sides are equal as well. So that would prove that OE, that side, is equal to OA. So it's equal to OA. And instead of saying angles opposite equal sides are equal, we'll say sides opposite equal angles are equal. Okay, so now that we got that, since those two sides are equal, then we already knew that. So again, I'm just going to tell them, but I already knew that OD was equal to OB, right? Those two were already equal. So that would therefore show us that DE is really equal to BA. Since this is equal to this, but these two were already equal. So there we go. It means that DE is equal to BA or AB. Okay, so there. Now that I've shown them that, I can continue using this now. I hope you guys see what's going on. Now I can continue using that. So I can go ahead and say, therefore, and I'm going to use the proportions we have here. I was just testing to see if it works here. So I'll tell them FO over FE, first of all. FO over FE is equal to, and I'm using TO over DE. So TO over DE. And the reason I can use this is because these were similar triangles. They're the proportions of similar triangles. Now I'm going to replace what I need to. So here I'm replacing FO with DO because I showed them that they're already equal. Okay, so I'm saying DO over, here I'm not changing FE. Let's leave it. FE, and then TO, we're leaving that and we're only changing DE. So let's go TO over DE, which we are changing now to AB because we have shown them that it's equal. So over AB. And now you just have to make it look like what they did. You see, so you compare first. When you find it and you find the reasons why other things are equal to that, then you keep it, you prove those things, and then you continue using it. So now, do you see that in theirs, they just left DO on its own. So I just have to find a way to leave DO on its own. To leave DO as the subject, you need to get rid of FE. So we can just multiply both sides by FE. So times FE, FE, and multiply by FE. Okay, so that would mean that DO is finally equal to, that cancels there, it's TO multiplied by FE over AB, just like they have it here. TO times FE over AB. And there we go. So that is it for this section. And that is it for this paper. So that's the paper 2, 2024, May to June, that is finally completed. Okay. All the best, matrix, for your exams. And you can go ahead and ask questions as well in the comment section. I'll do my best to get to it immediately I see them. All the best for your exams, and I will see you guys in the future videos. Bye for now.